Our topic is full adder. A full adder is a combinational circuit which adds 2 bits and also adds carry from the previous stage. Now the 2 bits of the full adder are A and B, and the carry from the previous stage is C in, carry in, and 2 outputs sum S and carry C out. Its block diagram is shown in the figure. In the block diagram, we have 3 inputs A, B and C in, and 2 outputs sum S and carry C. Now the truth table of the full adder is drawn. We have 3 inputs A, B and C in, and the 2 outputs sum and carry out. Because we have 3 input variables, therefore the total number of combination will be 2 raised power 3, which is equal to 8. Now these 8 combinations are 0, 0, 0, states of A, B and C input all are 0. Then if we add these 3, we will get sum 0, carry 0. Similarly, the second row is the binary code 1, which is 0, 0, 1. So if we add these 3, we get sum 1, carry 0. Similarly, the last term, which is a 1, 1, 1, if we add these 3, so we will get sum 1 and carry 1. Now we are going to write down the relation for sum and carry. So by writing, we will see the column of sum because we are going to write the relation of sum. So where in this column sum is 1, its corresponding minterm is written. Similarly, in the row at second, we have sum 1, corresponding minterm will be A dash, B dash, C in. Similarly, in the third row we have 1, so the corresponding minterm will be A dash, B, C in dash. In this way, all the minterms are determined, and then by adding all these minterms, we will get the relation of the sum. Similarly, if we want to write relation of C out, carry out, again we will see where is C out 1. Then we will write corresponding minterm, and in this way, by adding all these minterms, we will get C out. Now the relations are for sum S is equal to A dash, B dash, C in plus A dash, B, C dash in plus A, B dash, C dash in plus A, B, C. And for carry, we have the relation C out is equal to A dash, B, C in plus A, B dash, C in plus A, B, C dash in plus A, B, C in. Now we will simplify these relations by using K-maps. Because In the relation of sum, we have total 3 variables, so the number of squares of the K map for sum will be 2 raised power 3, which is 8. Similarly, in the relation of carry out, we have total number of variable is equal to 3. So the number of square will be 2 raised power 3. It is also equal to 8. Now we draw a K map of 8 squares, and then we have 3 variables. Along vertical direction we have A, and along horizontal direction we have B, C in. Now we will write 1 in the square, which should be according to the minterm given in the relation. So in the first row we have 1 in the second column. Similarly, 1 is written in the square which is in the first row and the last column. Similarly, other ones are written, and then we will see that no square is the adjacent square, no one square can be combined with any square, because these are not the adjacent squares. So the relation of sum will remains the same. Now for carry, we again write 1 in the corresponding square, which minterm is given in the relation. So then we can see that we can combine 2 squares because these are the adjacent squares. Now we have 1 in the first row's third column. Similarly, we have 1, 1, 1 in the third row, second column, third column, and fourth column. Now we can make groups of 2 each. First group is in the second row and column 2 and 3. Similarly, we make a group in this row which is in the column 3rd and 4th. Similarly, vertically we can make a group of 1, 1 which are in the third column, first row and second row, and then we will write the relation of the carry, and it will be the simplified relation. So the simplified relation of the carry will be carry out is equal to A carry in plus AB plus BC in. Now we will draw the logic diagrams for sum and carry out. So we can draw 2 types of logic diagrams. One diagram consists of AND gates and OR gate, and the other logic diagram which consists of the exclusive OR gate and the other gates. In the first diagram, we have 4 AND gate for the relation of the sum, because the sum relation has 4 minterms, and the first minterm is the inputs of first AND gate. Similarly, the second minterm is the input of the second gate, and so on. Now output of all the AND gates are connected with the input of the OR gate, and the OR gate will give us addition of all the minterms. Similarly, for carry, we have 3 minterms and simplified relation is implemented by 3 AND gates and 1 OR gate. Now the first minterm is the input of the first AND gate. Similarly, second minterm is the input of the second gate, and the third minterm is the input of the third gate. Now all the outputs of these 3 AND gates are connected with the input of the OR gate. Similarly, we can another diagram for the full adder circuit in which we use a 2 exclusive OR gate, and it consists of 2 half adders, because the sum relation for the half adder is S is equal to A dash B plus A B dash, which is also equal to A exclusive OR B. So A exclusive OR B can be obtained by using exclusive OR gate. Similarly, the carry relations is found by using 2 AND gates and 1 OR gate.